In this segment, we're going to talk about the signs of a geologically active planet. When we refer to geological activity, we mean that a planet's surface features and landscapes are being constantly changed. Processes that could cause these changes include volcanism, plate motion effects such as mountain building, and erosion processes. These are just a few of the processes that indicate that a planet is geologically active. Let's look at these individually. Volcanism refers to volcanic activity. In this picture from the Foundations textbook, we see Mount Etna erupting in 2001 above the Sicilian city of Catania. Notice you see lava flows. That's an indication of volcanism. Notice also you see this gas is being released into the atmosphere, another indication of an active volcano. Volcanism is one indication that a planet is geologically active. Let's look at another. Let's look at plate motion effects. To talk about plate motion effects, we must look at plates, and the plates only refer to Earth. Earth is the only planet that has plates. Let's look at the image or the map from nasa.gov. It is showing you, here's North America, here's South America, here's Africa, and here's Europe and Asia. Now notice that Earth is broken up into plates, and I've outlined the plates in red. Now the plates are labeled, so we have the North American plate, we've got the South American plate, you've got the African plate, you've got the Eurasian plate, and here's your Pacific plate, and your Indian Australian plate, and the Antarctic plate. And there are other plates, but these are your major large plates. Now that we've defined our major plates, let's talk about plate motion effects. One plate motion effect is mountain building. Now when two plates push against one another, you generate mountains. Here's a typical photo of a mountain from your textbook. So when two plates run together, you have this buckling of the plates and you generate mountains. In this diagram from your textbook, we see several mountain ranges. A very old mountain range is the Appalachian Mountains. A younger mountain range would be the Himalayan Mountains. You also have the Ural Mountains and the Andes. And this is where we had shown where the two plates were running into one another to create those Andes Mountains. So mountain building is just one effect of plate motion. Another effect is earthquakes. Now when two plates rub against one another, you create earthquakes, which is very common in the San Francisco region of the United States. So the rubbing of plates generates earthquakes. Another effect of plate motions is rift valleys. A rift valley forms when continental plates begin to pull apart. A good example is the Red Sea. Africa is beginning to pull away from the Arabian Peninsula, generating this rift valley. Here's a blown-up diagram from your textbook where we're looking at the two continental features being pulled apart, moving away from one another, creating the Red Sea, which is a rift valley. Another plate ocean effect is a mid-ocean rise. When plates spread apart and magma rises up, mid-ocean rises form. And the rocks that make up these mid-ocean rises are called basalts. So there's the location of your mid-ocean rise, and here it is in the bigger map. And here it is in the bigger map. There's your mid-ocean rise. Here's another one. Here's another one. Now, as we mentioned, these mid-ocean rises are made of basalt rocks. So what do basalt rocks look like, and what are they? Here's an example of a basalt rock. This is a golf ball-sized moon rock. It weighs 77 grams or about 2.7 ounces. And this is a lunar sample that comes from a larger moon rock that was collected by the Apollo 15 astronauts. The bigger rock was picked up on August 2, 1971, and was transported back to the United States from the moon. It is brownish gray in color, and it is classified as a medium-grained olivine basalt. Now, basalts are one of the most common types of rocks found on Earth, and it is also one of the main lunar rock types. This rock crystallized from magma erupted from the mantle almost 3.3 billion years ago and is predominantly composed of silicate minerals. Now, you're looking at this sample in an airtight, NASA-generated glass case that's filled with an inert gas. So you're looking at the rock, but it's in a glass case. But this gives you an idea of what a basalt rock looks like. It's a solidified lava rock. So there's our mid-ocean rise on our composite map. Another plate motion effect is the generation of subduction zones. Let's look at these. A subduction zone is a deep trench where one plate slides under another. As shown here, we have one plate sliding down under another plate. Now, the melting of that rock releases low-density magma that rises to form volcanoes, such as those along the northwest coast of North America, including Mount St. Helens. So here in this cartoon diagram, we're showing you that a volcano has formed, and this magma is rising up. Now, besides subduction zones, and rift valleys and mid-ocean rises and earthquakes and mountain building, another but subtle plate motion effect is erosion. So let's look at erosion. Erosion is the process of gradual destruction by physical action such as wind, water, or ice. Now, winds and water are ultimately traced back to volcanism, specifically from the volcanic gases that are emitted. These volcanic gases have water vapor in them. But the winds can't be just weak winds, they have to be strong winds. So let's look at winds first. Notice in this NASA JPL image these very long features indicating strong winds. We're looking at wind erosion features known as yardangs, which extend outward from the base of Olympus Mons, the largest volcano on Mars. So notice that wind can change the surface features of a planet. Another example is sand dunes, shifting sand in the desert. The surfaces are constantly being changed on the surface of Earth. Now, what about water erosion? A great example of water erosion is the Grand Canyon. The Colorado River began cutting the Grand Canyon only about 10 million years ago when the Colorado Plateau warped upward under the pressure of moving plates. A mile down at the bottom of the canyon lies rocks that are 0.57 billion years old. They are the rocks of an earlier mountain range that stood as high as the Himalayas. It was pushed up, worn away to nothing, and covered with sediment long ago. A third process of erosion is ice. A good example of ice erosion is glacier erosion. So this is a photograph taken by an astronaut on the International Space Station. And what we're looking at is the snout of the Uppsala Glacier on the Argentine side of the North Patagonia ice field. So here's a glacier, here's a glacier, here's a glacier, and this is the terminus point of the glacier. If you look carefully, you can see some moraine here, indicating slow and faster moving ice from the glacier. So think of it as like the boundary between the slow and the fast moving ice. So this portion of the ice in the glacier is calving, falling into the water. But if you look carefully, you can see this portion of an old glacier, and it's got this typical classic U shape here, indicating a glacier erosion. So the rock of the mountains were shaped by this slow-moving ice that you see here. Got the slow-moving ice down, and if you were to take away all that ice, you'd see this nice U-shaped valley, indication of glacier erosion or ice erosion. So volcanism and plate motion effects and erosion processes are just a few of the signs of a geologically active planet.